So on to page 3 of the study guide. Problem number 6 is where we're going to start. We are asked to use synthetic division to determine f of 5. So first thing I know is f of 5 means x is equal to 5. So that's what I'm going to use for the synthetic division is a value of 5 along with the coefficients here for f of x. So 2, -4, +1, -6, and 2. I don't need any placeholders here. First number drops, multiply, add, multiply, add, multiply, I believe, let's see, 155. I don't know how my pen just changed color. Let's try that again. 155. So add those up is going to put me at 149. And I think I have an idea what this is, but I also just am going to go ahead and pitch it into a calculator and double check. So 745, add that to 2, so 747. Okay, so that's my synthetic division. Now, with this function, all I need to know for f of 5 is this is equal to the remainder. That's the remainder theorem. So there we go. That remainder is the value for f of 5. It doesn't matter what the other numbers are. That's it. All right, problem number 7, we're going to do the same thing, but this time we know that g of -3 means x is equal to -3. So now I'm going to grab my coefficients. So -1, 7, 2, -3, -8. Okay, little workspace here. Drop that -1. So let's see. -3 times -1 is 3. Add that up. It's going to be 10, -30. So -28. -28 times -3. Let's find out what that is with a calculator. So that's going to be 84 plus -3 is 81 times -3, -243 plus -8 is -251. So g of -3 is equal to -251. Now I am going to double check that using just my regular function notation, replacing all of the x's with -3s, just to make sure I didn't do anything goofy along the way or lose a sign or a symbol. I did not. So problem number 6 and problem number 7, because it said to use synthetic division, you have to show me that work, so make sure you do that, okay? Problem number 8, determine if these two functions are equivalent. So this is kind of a review question from first semester. So what I want to do is take f of x, multiply this all out, and I'm going to do the same thing for g of x, multiply this all out, and then compare my functions at the end. So the first thing I'm going to do for f of x is to deal with this power. So -3x times x minus 2 times another x minus 2. Now, when I'm going to distribute, I can only distribute one thing at a time. So I'm just going to take this -3x times this x minus 2. So plus 6x, x minus 2. And I'm going to distribute now this -3x squared plus 6x to x minus 2. So let's see, -3x cubed plus 6x squared plus 6x squared minus 12x. So f of x is equal to -3x cubed plus 12x squared minus 12x. All right, so that's what f of x is. Let's see what happens if I multiply out g of x. So let's see, -3x cubed plus 12x squared minus 12x. Do they match? They do. So determine if the functions are equivalent. Yes. The functions are equivalent. And you don't have to say anything else other than that because your justification is the work that you showed here and here for distributing. So there's nothing else to do. Question number 9 is the same kind of question. We need to multiply out f of x. So I'm going to multiply out these two. So let's see what we get here. It's going to be x squared plus 5x minus 3x minus 15. And then this plus 2x at the end, it's not part of the multiplication, but I will need to include it when I combine like terms. So plus 2x. So speaking of like terms, we've got a few x terms here. So 5x minus 3x plus 2x. So plus 4x minus 15. And that's as simple as f of x is going to get. G of x, let's see what we get here. A little distributive property, but only at the end. So negative 15 plus 3x minus 2x squared. And then minus 8x. So g of x is equal to negative 2x squared minus 5x minus 15. Are these equivalent? Absolutely not. All right. Not equivalent. Hold on one second. I'm losing letters here. There we go. Equivalent functions. And again, your work is already shown, so you don't have to explain anything else about why they're not equivalent or are equivalent. Okay, so that's a little bit of a reminder from, I think it was sometime in first semester that we did problems like that. Problem number 10, part A and part B, solve the quadratic inequalities, graph the solutions, write your answer in interval notation. Okay, so what you need to do is start by getting one side of your inequality to be 0. So in the case of part A, I went ahead and subtracted 15. 15 was not like to either x squared or 2x, so I just wrote it out as part of the polynomial. I'm going to factor the left side of the polynomial. So x plus 5x minus 3. Each of these factors, x plus 5 and x minus 3, is going to create one of my x-intercepts, 1, 0. I'm going to find those by setting each factor equal to 0 and solving it. So x equals 3. Now, these are where my graph crosses the x-axis. So I'm going to sketch, and I do just a quick sketch. So somewhere over here I've got negative 5. Over here I've got positive 3. So this is my x-intercept, or my x-axis, sorry. Far left is negative infinity. Far right is positive infinity. There's a reason I put those on there. All right, I might need them for my inequality, my intervals. This particular quadratic has a positive a value. It's a positive 1, which means this is a concave up parabola. So there's my little parabola. And I want to know when this parabola is greater than or equal to 0. So I'm looking for anything above the x-axis, which would be greater than 0, or any numbers on the x-axis themselves. So those intercepts I actually want to include. So this is where I actually like having the interval here from negative infinity to negative 5, because that tells me where this starts. And then the other interval is from 3 to infinity. So I'm going to write those two out, and we'll talk about how we're going to write them in brackets or parentheses. So negative infinity to negative 5, union with 3 to infinity. If you have more than one interval that's joined, you put a little union symbol between them. Infinities will always, always, always in an interval take parentheses. Your numbers can take either parentheses or brackets. It will depend on what type of inequality we had. This particular inequality had an equal to portion. So because it's equal to, we are going to use brackets for our intervals. And those are the two intervals that work for graph A. We're going to do the exact same thing for graph B. So let me slide on over here to part B. I'm going to subtract 6 from both sides. So 3x squared minus 7x minus 6 is less than 0. I am going to factor 3x squared minus 7x minus 6. Now I'm going to do guess and check, and I'm going to do it relatively quickly because I've been doing this for a long time, and guess and check comes fast for me. But basically, if you needed to put it off to the side, and you can do the AC method, so 3 times negative 6, what multiplies to negative 18 and adds up to negative 7, you can absolutely do that. You will end up, or should end up, with the exact same factors that I do. If you don't end up with the same factors, something went wrong. So now using these two factors, I am going to find two x-intercepts. So let's see, 3x is equal to negative 2, which means x is equal to negative 2/3. It is absolutely okay to get fractions. Totally fine, nothing's wrong here. So if I go to sketch this, I've got positive 3 over here, negative 2/3 over here. My coefficient here, positive a value, so I have a concave up parabola. There we go. And in this case, I'm looking for things that are less than 0. So less than 0, I'm going to look for any part of my graph that's below the x-axis. So that's basically only between my two x-intercepts here. So negative 2/3 to 3, so there's no infinities to worry about. This particular inequality did not have any equal to portion to it, so you are going to use parentheses to enclose your interval. All right, so problem number 10 is done, both parts A and B. Last part for this particular video is the end behavior for number 11. This is a throwback to, I think, the last unit that we did before break, or the unit before, I forget which. But the idea here, we've got a positive a value with x to the 4th. So that particular curve would look something like this, kind of the basic shape. There can be some mountains and valleys in the middle, but ultimately it's concave up in both the positive and negative direction. So end behavior, as x approaches infinity, f of x is also approaching, so infinity for x is to the right, and as we move to the right, this graph is increasing to positive infinity. As x approaches negative infinity, f of x approaches, well, negative infinity for x is going to be to the left. As we move to the left, the graph is going up to positive infinity. So those are the two lines for end behavior for part A. Let's see what end behavior for part B looks like. So m of x here has a negative 7, so my a value is negative, but this time I'm dealing with an odd degree polynomial. So if I were to sketch this, I would start high and curve down to low. So something maybe like this. Doesn't have to be exactly that. Again, there can be mountains and valleys in the middle that I'm just not paying any attention to for end behavior. So as x approaches infinity, m of x approaches. So as we move to the right, my graph is dropping, so that's going to be to negative infinity. And as x approaches negative infinity, m of x approaches. So as I move to the left on my x-axis, my graph is increasing to positive infinity. So remember, for end behavior, your even degree functions, the end behavior matches. Now they don't have to be going to infinity, but they both have to be going to the same place. So either both positive infinity or both negative infinity. And your odd degree functions, your end behavior is mismatched. So one's going to negative infinity, one's going to positive. All right, so that's the end of page 3. If you've got any questions or concerns, let me know.